Hi, this is Mr. Sanders, and I'm going to give you a quick tour through some of the work that we did earlier this week. Here's a list of the special right triangles, the 30, 60, 90 triangle, and the 45, 45, 90 triangle. 30 degrees, 60 degrees, and 90 degrees. This is the layout of the angles. And when you take any triangle that has 30 degrees, 60 degrees, and 90 degrees, the ratio of the sides is always in this specific relationship. The side opposite 30 degrees has a value of 1, and the hypotenuse is twice as long. So if this was a 3, this would be 6. Here, this side, which is opposite the 60 degrees, is a bit longer than 1, and it's shorter than 2. It has the value of the square root of 3. And the square root of 3 is approximately 1.78. So these are the relationship or the ratio of the sides for a 30, 60, 90 triangle. Later what we're going to do is we're going to ask ourselves, what's the value for this side opposite the 60 degrees and this side opposite the 30 degrees if we want this side to be equal to 1? And we'll ask the same question about this. The reason is we want to fit both of these into a unit circle. 45, 45, 90 degrees, that means this side, this angle here is 45 degrees, this angle is 45 degrees. The two angles are equal, so the sides are equal. They have a relationship of 1 to 1. This is part of a square, so this side here, using the Pythagorean theorem, comes out to be the square root of 2. If we want to put the special right triangles in the unit circle, then the hypotenuse of the triangle has to be equal to the radius of the circle, and we want that to have a value of 1. To change the 30, 60, 90 degree triangle into one that fits into a unit circle, we need the hypotenuse to have a value of 1. That means dividing this side and the two legs, divide the hypotenuse, the two legs, by 2. Dividing by 2 gives us a hypotenuse of 1. The side that had a 1 is now 1/2. It still has a relationship that this is double this length. And this side here, opposite the 60 degrees, has a numeric value of the square root of 3 divided by 2. Now we have a radius of 1 and a hypotenuse of 1. We'll be able to put that into a unit circle. The isosceles right triangle, 45, 45, 90, which traditionally, when we look at it and reduce it down to the smallest numbers, the hypotenuse has a value of the square root of 2. The legs each have a value of 1. Dividing by the square root of 2 would turn this hypotenuse into a hypotenuse with a length of 1. Square root of 2 divided by the square root of 2 is equal to 1. We have to do the same thing to the legs. We end up with a hypotenuse which has the length of 1, the same as this one. Both of these are radii in a unit circle. Both of these triangles will now fit into the same circle, but this is the radius, but the lengths of the different sides now have these values, 1 divided by the square root of 2. And we can leave it just like this. We don't have to do any more calculations. All right, I switched easels. In this case, here is our isosceles right triangle in a unit circle. The circle has a radius of 1. This value, the leg of this triangle, is shorter than the radius, but the hypotenuse is a radius for the circle. So this length is 1. What we said earlier is that means that the legs have a value of 1 divided by the square root of 2, 45 degrees. This is also 1 divided by the square root of 2. And then what we want to do is take the 30, 60, 90 triangle, put it into the same unit circle, because we're going to look at the 30 degree angle here. This 45 degree angle is larger, so this is what it looks like. Here we have the 30 degrees. There's the 60 degrees. And adding 15 degrees gives us 45 degrees. And here's the 45 degrees. 45 degrees is larger than 30 degrees. Therefore, the opposite sides are in relationship to the size of the angles. The larger the angle, the larger the opposites, or the longer the opposite side. So at 30 degrees, the side we calculated has a value of 1/2, right here. And we know that the 45 degree angle is larger, therefore this side, which I've labeled as EF, is going to be longer than this side, which I labeled as DC. DC is the sine, or the opposite side, of the 30, 60, 90 triangle, which is here in blue. DC is going to be shorter than the side opposite the 45 degree angle, EF. So we can write it as line segment EF is greater than line segment DC. We have this value as 1/2, and from the work we know that this is 1 divided by the square root of 2. Not looking at this at the moment, we can say that this is true because we can see the sides here geometrically. The value of 1 divided by the square root of 2 on a calculator is approximately 0.7076, and that is in fact greater than 0.5. The two triangles are in the same unit circle. We could do this kind of calculations with other triangles so that we can learn more about the relationship of right-angled triangles to the unit circle. We'll use this information as we start to study what happens here on the circumference of the circle. As we go around, as the angle increases, what can we tell about a point that's on the circumference? For example, point D and point E. We could start to think about how far this point has traveled from here to here, or all the way around the circle.